We put a lot of trust in data to make fair decisions, everything from who gets into college to who gets a promotion. But what happens if the very tools we use to prevent bias are themselves deeply flawed? Well, today, we're going to pull back the curtain on a hidden assumption that is almost always overlooked, and it has some massive, real-world consequences. Okay, so let's just start with the most important question of all. Imagine a company is rolling out a new test for promotions. They have to be sure it doesn't give an unfair advantage to one group over another. And this isn't just about ethics, it's often a legal requirement. So, how do they actually prove it? How can we be sure the numbers aren't secretly telling a biased story? All right, here's the game plan. We'll start with why this question of fairness is so high stakes. Then we'll introduce the statistician's favorite tool for the job and uncover the hidden, fatal flaw at its core. From there, we'll see the damage it can cause, why a common fix is actually worse, and finally, what this all means for you and me. So, let's really set the scene here. An organization has a test. They want it to predict who will be good at a job. The goal seems simple, right? A high score on the test should mean you'll be a high performer, no matter who you are. But the stakes are just incredibly high. We're talking about people's careers, their livelihoods, and the basic idea of equal opportunity. Now, the technical term for the landmine they're trying to avoid is differential prediction. It's a fancy way of saying the test works differently for different people. For example, maybe a score of 85 points to great success for a male applicant, but only average success for a female applicant. If that's happening, the test is biased, plain and simple. And using it could lead to serious discrimination. Getting this right is a huge deal. So, how do you even hunt for a sneaky bias like that? Well, for decades, the answer has pretty much been one single powerful statistical tool. It's been seen as the gold standard for figuring out if a test is playing fair. It's called moderated multiple regression, or MMR for short. It's a pretty slick method that basically asks one question. Does a person's group membership, say their gender, change how well their test score predicts their job performance? It's designed to give you a clear yes or no on whether the test works the same for everyone. And for a long, long time, this was the way to get that answer. But this is where our story takes a sharp turn, because this trusted, widely used tool is built on a crucial assumption, an assumption that, as it turns out, almost nobody checks and is very often wrong. This right here is the hidden flaw that can throw the entire search for fairness completely off the rails. So to get this flaw, we have to talk about something called error variance. Now stay with me, it's way simpler than it sounds. Imagine two archers. On average, they're both equally accurate. Their average shot hits the bullseye. But the first archer's arrows are all in a tight little cluster right around the center. The second archer's arrows are all over the place, but they average out to the bullseye. That scatter, that's the error variance. It's just a measure of unpredictability. And here is the giant catch. For MMR to actually work correctly, it has to assume that the scatter is the same for every single group you're comparing. It's a principle called homogeneity of error variance. Basically, it assumes both of our archers have that same tight arrow grouping. But what if they don't? What if one group's results are really predictable and the others are scattered all over the target? Now take a look at this. This is what you see when you plot all the data. Everyone, all lumped together. And it looks great, right? You see a clear, positive line. Higher test score, better job performance. You'd look at this and think, perfect, this test works. Everything seems to follow one simple, clean rule. And this is the moment of truth, the smoking gun. When we split that same data into subgroups, males on the left, females on the right, the problem just leaps off the page. Just look at the graph on the left. See how widely those dots are scattered? Now look at the graph on the right. See how much more tightly packed they are around the line? That difference in scatter is precisely what MMR assumes cannot happen. The whole analysis is broken before it even starts. Okay, so what happens when you apply good math to a situation that violates its most basic rules? Well, the consequences are not just academic. When researchers ignore this difference in scatter, the test can get things spectacularly wrong, leading to two really dangerous kinds of mistakes.
These are the two big dangers. First, you have a type 1 error. Think of this as a false alarm. You might conclude a perfectly good test is biased and throw it out, which is a waste. But the type 2 error, that's the missed threat, and it is so much worse. This is when the math tells you a test is fair, when in reality, it's not. An organization could go ahead and use a discriminatory test, causing real harm, all while thinking the statistics gave them the green light. So you're probably thinking, how often does this really happen? Is this just some rare theoretical problem? Nope, not at all. A review of published studies using this exact method found that a staggering 19 out of 20 of them violated this core assumption. Let that sink in. 19 out of 20. This isn't some tiny little issue, it's practically the norm in the research we rely on.
So, naturally, some researchers did notice this problem, and they came up with a fix. It's a mathematical tweak called an inverse data transformation. It's designed to kind of force the scatter for all the groups to look equal so that MMR is happy. Sounds great, right? A simple solution for a tricky problem. But, as we're about to see, this so-called fix is way worse than the original problem. The authors of the paper we're looking at use this incredibly powerful phrase to describe that fix. So why is it so dangerous? Because in trying to correct the math, this remedy doesn't just nudge the data, it fundamentally changes it. It ends up destroying the very truth you were trying to find in the first place. This table really says it all. Look at the top row. With the original raw data, the conclusion is that an interaction exists, meaning there might be a real difference between the groups. But look at the bottom row. After the data is transformed to fix the scatter problem, that interaction completely vanishes. The remedy didn't uncover the truth, it literally erased it. It's like changing the evidence to fit your tools instead of the other way around. So, where does all this leave us? We've seen that the standard tool for fairness has a hidden flaw, and the common fix for that flaw is a total disaster. And it really highlights a crucial point. The statistical choices we make are not neutral. They have profound, real-world implications for justice and equality. At the end of the day, these statistical methods aren't magic. They're just tools and they have rules. When we break those rules, like ignoring that unequal scatter, we risk making a terrible decision. We might throw out a fair test, or worse, approve a biased one. And as we've seen, rushing in with a quick fix can make everything even worse. True fairness requires using the right tools for the job. Now, the good news is there are better ways to do this. The researchers point to other methods, things like non-parametric tests that are much more robust. These tools are designed to work even when the data isn't perfect, when that scatter isn't the same for everyone. They don't need to make this flawed assumption to begin with, which makes them a much safer bet for answering these incredibly important questions about fairness. You know, this whole investigation into one little statistical assumption really shines a light on a much bigger truth. The algorithms and data models that increasingly run our lives, from hiring and credit scores to medical diagnoses, are all built on a foundation of assumptions. So the question I want to leave you with is this. If a flaw this big can hide in plain sight for decades in a trusted scientific method, what other hidden flaws are out there in the data that shapes our world? And what happens if we never find them?